afternoon, everyone. My name is Tanya-Leveraging. I'm from the Faculty of Civil Engineering at the Technion in Israel. I know it's a difficult time for a lecture after lunch. I'll try not to bore you too much. The paper that I will be presenting is titled Leveraging Graph-Based Semantic Enrichment for Enhanced Automated Code Checking. This is the agenda. So I will first of all give you a very short background and try to explain the motivation for this work. I will then talk about the concept of semantic enrichment and how we envision it being incorporated into the automated code checking workflow. And then I will present a test case where we have focused on two different semantic enrichment tasks that we handled by two different graph-based solutions. And then some results, discussion, and conclusions. Okay, so there are two main concepts within the idea of automated code checking. We have the regulations on one end, and these are text documents that have to be somehow translated into the machine-readable representations. On the other hand, we have the design, and the assumption here is that the design is given as a B model. So in a way, we can say that this is already machine-readable, except that we know that these models are not perfect, that there is information requirements that are very specific to the code checking aspect, regulatory concepts that are usually not explicitly presented in these B models, and they have to be supplemented. And again, the common practice is just doing it manually. And so this is exactly where semantic enrichment can be useful, because basically what we are saying is that we can automatically infer and embed the B models with the required information to allow the comparison between the design and the regulations in a way that does not require any further interpretations or basically any additional manual work. So the test case that we focused on comes from the Israeli regulations for security rooms, for bomb shelters basically. Starting from 1989, it became mandatory that within every dwelling unit, there will be a security space, a security room. And there are lots of regulations as to how to design them and how to construct them. One of them is that these spaces have to be stacked one on top of each other to create a security shaft, which is entirely made out of reinforced concrete. And the walls of that shaft have to be continuous and reach the structural foundations. And one of the problems is that many times on the lower levels of this residential buildings, we see, for example, parking lots, we see storage, we see public facilities, and these walls are simply in the way, they interfere. So the regulations do allow to remove some of the walls. The preferred situation is that if you look at any space within the security shaft, at least 70% of the walls surrounding it have to be continuous and reach the foundations. But you can also have between 50 and 70%, and you can even have less than 50%. Each of these categories then determines its own set of conditions and requirements that have to be followed. One of them is for the minimal thickness of the structural elements within the shafts, and this is what we focused on. This is the model that we've been working on. This is our test case model. It also comes from the Israeli industry. So you can see this is a residential building. We have 5 apartments per floor, which means that we have 5 individual security shafts that have to be checked. And what makes this thing challenging is that we have these 2 additional underground parking levels where obviously some of the walls have been removed. So we began by trying to figure out what are the information requirements, or what is the information that we must have within these models, but we usually do not get from the models that we get from the industry. And the most fundamental thing is actually identifying the security room. So there are no naming conventions in Israel, so you can extract pretty much anything out of the tags in this model. So we wanted to identify it automatically. And there is some previous work about exactly this, about classifying room types in residential apartments. The problem is that it assumes that we operate within the boundaries of a single apartment. So it assumes we are able to isolate an apartment from a floor plan, which is actually also a piece of information that we don't really have in the model. So what we did, we tried to use an algorithm for community detection to identify those groupings that represent the individual apartments. So first of all, every floor plan was translated into the topology graph representation, and this happens using Dynamo inside Revit, so this is automated. Once we have these representations, we implemented the German-Newman algorithm for community detection, and we were able to identify the isolated groupings within this large graph that actually express the individual apartments. Once we have that, we could easily implement the previous work and to identify the security rooms correctly. The second task, semantic enrichment task that we handle maybe with even much more detail is the classification of spaces based on the ratio of supporting walls. So as I mentioned before, this is very meaningful information, and this is today performed manually. And the problem is that this calculation is very complex because there are lots of guidelines in the regulations as to how to calculate, but there are also lots and lots and lots of exceptions. Just to give you an example, sometimes a wall that has an opening in it will be calculated in this ratio of supporting walls, sometimes it will not. And it doesn't just depend on the size of the opening, it also depends on the location of the opening in relation to other openings on the same level. So there are lots of topological considerations here between the elements that have to be taken into account. And the most interesting thing is that we don't really care about the end number. It doesn't really matter if it's 70, 75, 95, or 100. We just need to figure out for every space within the security shaft, which of these three categories it belongs to. So this is how we treated this. We treated this as a classification task instead of a calculation task. And the way that we are doing this is with graph neural networks. So a machine learning model that operates on graph. Sorry for my voice today. Again, the idea being is that since there are so many considerations about the relationship between the elements within the security shaft, we have to somehow express that within the machine learning model, and we can do that with a graph. So the first thing to do was to actually get this vertical graph that represents the security shaft, and this was again done using Dynamo inside Revit. This time we basically analyzed the intersections between the bounding boxes of the security rooms that we have already identified to the other elements in the model. And the elements that intersect that then were collected into this graph representation where we have spaces, walls, windows, and doors as nodes on the graph, and then the edges represent the relationships. One of the main challenges that we had with this is training. So GNNs, graph neural networks, they are supervised machine learning models. They have to be trained. In this case, we generated our own data set for training manually, and we had the help of one of the building control companies in Israel to do that, to identify the possible design variations, because the idea was to really mimic the real world as closely as we could. We ended up with 710 beam models of such security shafts, which then were also translated automatically into the graph representations and used to train a GNN model. In this case was the graph attention network for node classification. This is kind of the final envisioned workflow. So we're basically saying, okay, we will pre-train the GNN before the check. Once we get a model that has to be trained, it is first of all being enriched with the information about identifying the security rooms and with the information that is the result of the GNN. The result of the GNN, this ratio of supporting walls, that actually activates the proper rule set that then has to be applied, because as I explained before, each of these three categories determines their own set of conditions. So the result of the GNN activate the proper rule set that is then applied to the model, and we get the results. Just a few things that I want to note about the GNN. So what you can see here is the confusion matrix of the prediction results of the GNN model on our test case model, the residential building with the 5 shafts. And you can see that there are 4 classes here instead of the 3, and the reason being is that because we also had openings represented as nodes in the graph, so they are also being classified. So we had to introduce this not applicable label, 4th label, to handle this classification. And one more thing that I want to note is that individual walls, they are also nodes in the graph, so they are also being classified. And while this is information that is kind of irrelevant to this specific check that we are doing, there is actually a section in the code that discusses the allowed shifting, horizontal shifting between the walls of the security shafts, where this information is very meaningful. So you can say that this one semantic enrichment task, we can actually support 2 different checks of the regulations. Back to our task case model. So as I said, we had 5 security shafts that had to be checked, total of 265 walls, slabs, and so on were checked using the proper rule set, as I said. The result is that we got 27 false positive cases, meaning that these are elements that are compliant to the code, but they were wrongly tagged as not compliant. What's more important is that we got 0 false negatives. So basically all the problems within this model were identified correctly. There were 19 issues in the test case model. All of them were identified. Conclusions. So yes, this is still machine learning. It is not deterministic. So we cannot claim this would be the accuracy for any single test case that we try. For all the regulations and all the scenarios, this all has to be continued and tested. There's still lots of work to be done also to improve the models, the basic models, and so on. So we cannot claim that these would be the accuracies of results every time. But I think that the result of the GNN and the result in the accuracies is actually not really the point of this work. I think that the most important contribution here is that it opens up a new direction of thinking about automated code checking, and instead of confining the entire process into rules, we can start thinking about methods where we combine different methodology, different approaches to solutions to get a process that is more highly automated. That's it. Questions?